So, last time we looked at how air resistance force can be calculated, but today we're going to look at how the air resistance force can affect the motion of an object travelling in a parabolic path. We're not going to do it mathematically because it turns out to be quite complex. If you remember that the air resistance is proportional to the velocity squared, if you think about it carefully, then as an object is travelling through its motion on its projectile path, its velocity will always be changing, and therefore the air resistance force will always be changing as well. And then you can realise that it's not going to be a constant acceleration, and that becomes quite difficult to work with, and we need some calculus. So we're just going to do it descriptively, and to start with we're going to look at how the motion is affected in the horizontal and then how the motion is affected in the vertical. Just like when we're analysing projectile motion, we divide the components up into the horizontal and the vertical. We're going to do the same here. So let's have a go. So with the horizontal motion, the air resistance, remember, acts to oppose the forward motion, and if an object is travelling horizontally and something, in this case it's air resistance, is opposing the motion, then that's going to slow the velocity down in the horizontal direction, okay? And so we're going to get a deceleration, and rather than when we were analysing projectile motion, we thought about without air resistance, therefore the horizontal has a constant velocity. This time the velocity is not constant, it's slowing down. And you can see if the velocity slows down, then we're not going to get as far in the horizontal direction. The object will fall short of the full range without air resistance. Okay, so we can say in the horizontal, the reduced, as the velocity is reduced, then the range will be less. So that's the horizontal motion. That's fairly straightforward. But what is happening in the vertical? And this is where we have to do a little bit more thinking, because it turns out that the upward motion is affected differently than the downward motion. So in the vertical part, we're going to look at the upward and the downward motion separately. Okay, so the object is moving up like that, and in what direction did we say the air resistance is acting? Alright, that's right, it's acting to oppose the motion. So the air resistance force on the way up is acting downwards. Okay, I'll give it the symbol FR for the force of air resistance, okay? And the force of air resistance is acting in the opposite direction to the motion of the object up, okay? But we have another force also acting in the downwards direction, and that is gravity, okay? So we have the force of gravity and the force of air resistance both acting down on the object. And what do you think that's going to do? It's going to increase the downwards force, therefore reducing the height, or the height to zenith, that the object is going to reach. But not only is the height reduced, as we can see in our first diagram there, okay, not only is the height reduced, but also because it doesn't go as high, then the time is also less on the way up. That's the upwards motion. What about when it comes back down again? Okay, and you can see my little man there with the parachute and he's coming down or she's coming down, and with a big parachute there's going to be significant air resistance. On the way down, which direction is the air resistance acting? Right, it's acting to oppose the motion, which is upwards now. So that's why we have to break it up, because when it's falling, the air resistance is pushing the other way. But you can see the force of gravity is still acting downwards. Alright? So now, instead of the forces acting together, like on the way up, alright, the forces are now opposing each other. So this actually reduces the force, the total force acting on the object as it falls. So if you've got a reduced force, then we know by Newton's second law, alright, Newton's second law, force equals mass times acceleration. If we reduce the force, then we're going to reduce the acceleration of the object. And so our parachutist is going to descend less rapidly, thus increasing the time. Okay? The total force is now less, and therefore the time of flight is going to be longer on the way down. Now, I'll mention one more thing here. You may or may not pick up that if these two forces if the force of gravity and the force of air resistance actually end up being the same, alright, then what's the total force going to be? Well, if they're opposing and they're equal, then we have a zero net force. If you have a zero net force, then you're going to have a zero acceleration. So we reach what's called terminal velocity. When those two forces are equal, the downwards and the upward force of air resistance are equal, we reach terminal velocity. And the object can't get any faster. So for our parachutist up there, okay, I think with a parachute open, they might be going maybe 40 kilometres an hour, depends on the parachute. Without the parachute, it's much higher. It might be around 200 kilometres per hour. So surviving a fall without a parachute is pretty difficult. It's like running into a wall at 200 kilometres an hour. Alright? Some people have managed to do it. There's one other thing we need to mention, and that is what happens to the overall time of flight. Okay? If we compare the time of flight without air resistance compare the time of flight without air resistance to with air resistance, we will find that the total time is slightly reduced overall. Okay, we don't need a mathematical proof of that, but it is something that you need to know, that the overall time of flight is slightly reduced. So you can see that there. Alright, we'll see you next time.